Hi everyone, welcome to this sixth in a series of meeting that we have organized to introduce the new Turing Fellows. And it is my privilege today to introduce Dr. Alex Casson and Professor Will Dixon. So both speakers will have 20 minutes and then there's going to be 5 minutes for Q&A. And we're going to start with Alex. Alex is reader in the Department of Electronical and Electric Engineering. And the title of his talk is Data Science and Machine Learning for Wearables. So Alex, the floor is yours.
Oh, thank you very much. So just checking, you see the slides okay there? Yeah, super.
Yes, we can. Yeah.
Right, so thank you very much for the opportunity to speak to you today. So I'm going to talk about some of my work in wearable devices and particularly the machine learning aspects of that. I would like to kind of put the acknowledgements at the start of a presentation rather than kind of forgotten about at the end. But of course, the work you're going to see is the result of lots of collaboration across different groups across the world and lots of different funding sources, just to kind of acknowledge those there. I mean, actually, my background is in wearables, which in some ways today are kind of mature, commercially available technologies. And I think we're going to hear more about this in Will's presentation next about how some of these devices are actually being used in health and social care. I'm in electronic engineering, so my interest is more in the kind of devices themselves, about how we make them more functional, how we make them meet user needs better, and so on. And for people who've used wearable devices, there are, of course, a wide number of open opportunities in terms of how we make them better and more functional. There's lots of questions about the kind of accuracy of devices. We get feedback from nurses in particular about battery life. There's a lot of battery changing, battery charging that is still needed to go on. And then just integrating systems with the healthcare system, tackling issues like privacy and so on. So I aim to kind of tackle some of these challenges from the engineering kind of point of view. So what we've got on the screen now is kind of my cross-section of a wearable device. So kind of how we get data from you know, the biological world, up into ultimately the cloud, where we can put the data wherever we want, do whatever sort of large-scale processing it is that we want, and then potentially back again for treatment or intervention. That might just be kind of behaviour change, you know, with your Fitbit encouraging you to exercise more. It might be more sophisticated than that. But I started in this area probably about 15 years ago, a little bit more than that actually, very much looking at the low-level electronics. How do we make low-power devices that are feasible to fit in to this very miniature kind of form factor? And so kind of that work predates, you know, the Apple Watch, Fitbit, and so on. If we jump to my lab today, we've got activity across that entire spectrum. So there are different things going on in each one of the different boxes. I'm probably better known these days actually for my work on the left, towards the left-hand side, around making electronics not on traditional rigid substrates, but making things that are flexible, that can strand and kind of bend down the body, and kind of conformal electronics, so they're kind of more comfortable and so on. But of course in this talk, we're going to be focusing on kind of activities much more towards the right-hand end. So one about the kind of signal processing, the data analysis, which of course is a key part of a complete sense actuate system. You know, ideally we want to be collecting data, doing something with that, and then doing something with the person. By and large, I'm not running a data science group. You know, if normally the kind of machine learning that I would be looking at is constrained in some ways, and I'll come back to that a little bit later. So often we're looking at low power situations because you've got to run on a wearable device with kind of a small battery, or we've only got a limited time in which to kind of make a decision. And yeah, there are other groups who are specializing just for kind of large scale big data analysis type of stuff. Although of course that is where we would start, because for all of our constrained machine learning type stuff, we start with a prototype that we would implement in the cloud on HPC or wherever. So just before getting into some of the machine learning, just to highlight some systems for people on the call. People often come to my group if they're interested in making a bespoke device. If there's something that people want or need to measure and aren't able to do at the moment with an off-the-shelf device. So here we've got some examples of different systems that we've made in recent years. The one on the right isn't wearable, obviously, but the others are all different kind of custom-made wearable sensors to pick up boxes that we can't get with off-the-shelf devices. And then as I said, we've got a lot of activity in my lab about flexible electronics. So making devices that can get better, longer term attachments to the body. So we sometimes talk about kind of artificial skin layers. So epidermal electronics, something that sits kind of with the skin rather than a wearable kind of on top, as it were. And then a lot of people also come to my lab when they want support in using wearables, which is sometimes as simple as just advice on which systems to use. And of course, there's lots of considerations there about information governance and where the data is going. And often for your research study, a Fitbit, whilst it's well known, may well not be the best choice. Something which keeps the data local to the person has a much clearer information governance case. And then I say we might help with some of the data analysis there before really passing over to a big data type group. I'll highlight this slide at the moment. Just, where I'm mainly doing that right now is for 2 long COVID works with different parts of the NHS. That's where a lot of our wearable support is going at the moment. And then in terms of the bulk of this presentation, I picked out, I think it's 3 different areas about the kind of data science and machine learning that I've been looking at with my team in recent years to go over with you. So the first of those is analysing data in the UK Biobank. So if you're not familiar with it, the Biobank was established, I think about 2009 or so, and they collect a very wide range of different samples. So there's lots of, say, blood samples and so on, from about 500,000 people in total. So there's a huge amount of data that has been collected as a resource for data analysis. There's lots of genetic type analyses that are being performed on the UK Biobank. The Biobank has also performed some wearable data collection. So they got about 100,000 people to wear a wrist-worn accelerometer device for measuring different levels of activity. And in some ways, this is a really fantastic resource. We can use this to do large-scale analysis experiments without having to collect data ourselves. It's not realistic for one lab to collect data from 100,000 from 100,000 people. And so and there's also then a lot of metadata that's been collected with this. So people did questionnaires about their mental health, for example, about whether they've got any skin conditions, arthritis. There's lots of coding data that we can use to kind of help kind of correlate with the activity data that is recorded. And so we've done work looking at analysing the 100,000 records that we get. Now, that's actually been surprisingly challenging. I gave a dedicated presentation on this, I think in about June last year, and it's on my YouTube channel if you wanted to search for it. If you're interested in using the biobank data, this is going to be changing a little bit, but in the university, we downloaded a copy of the accelerometer data. And one of the aims there was that to be an institutional version that we could help other people to use and kind of accelerate. But there are lots of kind of gotchas. There are lots of things to be aware of that mean that what you think might be a good analysis isn't actually a valid analysis to do. So, for example, having said that there's lots of metadata available in the biobank, a lot of it was collected over a long period of time. So there may well be 4, 5, 6 years between your metadata and the activity, the wearable data collection that somebody did. And so you can't assume that somebody keeps the same weight. You can't necessarily assume if somebody's got a fluctuating condition that they still have the same health condition that they did X many years ago. And if you're not aware of some of those gotchas, you can easily end up with an analysis which is correct in some senses, but not in others. So if you are thinking, if you're in the university and are thinking of analysing the biobank, the accelerometry data in the biobank, I would encourage you to get in touch, and we've been helping a number of people through this process. Or as I say, we've got a dedicated presentation on the YouTube channel about analysing that. What we were looking at in particular was how can we use some of the things we've learned from doing this big data collection experiment for improving wearable devices. So, and in particular, we did that for looking at what's called energy harvesting. So there's long been a kind of a dream of the kinetic watch. So your self-winding watch, there's no battery, it just collects energy. If I wave my arm around, it kind of winds itself up, and you never need to worry about charging it, and so on. If only you've got a watch mechanism, that's quite easy. We've had kinetic watches for a long time now, but just a watch mechanism is very low power. I mean, for a basic wearable set of electronics, you probably need at least 100 times more power than you would need just to have a watch mechanism. And so what we looked at is, how much energy can we harvest? If we look at the amount of activity people are doing, how much waving of their arms are they doing? How much energy will that let us collect? Is it going to be feasible for powering our devices? We looked at this at a total of 67,000 participants. So by the time we'd got rid of people who didn't have it on for long enough, we had to get rid of several thousand people. But as far as we can find, the previous larger study looking at energy harvesting had 20 people. So it's always nice when you can get several orders of magnitude on advancing the state of the art. Because we can look, with so many people, we can look at how does the energy harvesting potential vary between people across time of year, is it summer, is it winter, between different disease conditions, and so on. So as I said, we've made available our open source framework for doing this, and this is kind of optimized for running on the high performance computing resources here at the university. So do take a look at that if you're interested. But then just to go over some of the averaged results, we can see coming out very clearly roughly how much harvestable power is quantified on this graph we can get for different participants. Slightly more for females than it is for males. We can break down how that differs for different age groups. And perhaps unsurprisingly, as people tend to age, they are moving about less, and we can collect less energy for powering our device. So if we're looking at an aging population and making wearables for that, a self-powered wearable becomes harder the more you're looking to make it fit your use case. We can also see quite nicely on the upper graph there that people have a nice lie-in on a Saturday and Sunday. The activity is clearly starting as an average across the population much later. And then we can break that down into subgroups. So here we've got a control group and a matched group of people with diabetes. And we thought diabetes was a condition that was unlikely to go away. People do sometimes enter remission, but most people, once they've got a diagnosis of diabetes, they have it. And again, we can see very clear differences coming out here. So again, if we're saying we're interested in self-powered kind of wearable devices to help people with whatever their medical condition is, of course, actually we're seeing that we're getting less harvestable power when we're using it in the population with whom we want to use it. We see other patterns coming out from that. So we also looked at kind of shift workers versus non-shift workers. Obviously very different patterns of activity overnight versus not overnight, and we see lots of statistically significant differences there. And of course, the aim from my point of view now would be to use this information to drive power opportunistic sampling. So doing the wearable sensing that we want to do, doing the transmissions, the power intensive operations when we're likely to have power available to do it. Second topic I was going to touch on, and we've only got 5 minutes left, was closed loop neuromodulation. So when people think about wearable devices, they tend, these things tend to go in an order. The first thing always tends to be activity sensing, because I think from the technological point of view, it's the easiest thing to do. A bit after activity sensing, heart sensing came on board, and nearly all modern wearables would include wearable heart sensing. And there's lots of work now in getting other modalities into wearable devices. My lab's done a lot of work on brain interfacing, so trying to take kind of full head montages, things that really look like you've got on the screen here, and making them into small portable devices that people would be willing and able to kind of walk down the street wearing. But that use case is one where we've done a lot of our work about closed loop interventions. So my lab, we don't do so much stuff about behavioral changes. We're not a behavioral lab, but we're interested in what kind of technological interventions could we give to somebody. So typically this would mean monitoring somebody's data in real time. And then if we detect something has happened, stimulating the person as a result. So trying to do, sometimes it's called bioelectronic medicine. So doing some form of a stimulation rather than giving them an exercise regime or a pharmaceutical to take. Now, the big challenge in doing this is what we have on the right-hand side here about low latency signal processing. Because when we stimulate people, what we get normally are artifacts in the recording that we're trying to do at the same time. And so what we've got an example of on the screen here is brain data being recorded while we're stimulating the person. And what it's meant to, what we're meant to have is nice clean data, and actually all you see is stimulation artifacts. So we've got to do some rapid signal analysis to get rid of those artifacts so that we can make a decision on what to do in the stimulation. And typically we maybe have kind of 20 milliseconds or so for doing that. So we just don't have time to send data up to a data center, make a decision, send it back again. The processing has got to be much more local than that. And we've investigated, what this slide is doing, saying we've investigated that for a number of different modalities. What I'm going to talk to you about is about electrical stimulation, but we've also looked at lots of different forms of sound stimulation, visual stimulation. I've not done any magnetic stimulation, but there's lots of similar work there. One of the key needs in this space is about verification, right? So the machine learning I've done in this space isn't actually about removing the artifact. Well, we have done a bit of work on that, but we've not published it yet. Actually, we're using classical signal processing for doing the artifact removal. Fundamentally removing the artifact, going from this sort of sinusoidal trace to nice clean data, isn't that hard. There's quite a number of different techniques that will give you nice looking data. The challenge is much more verification. Because normally we don't have a ground truth, so we don't know what we were recording because it was obscured. That's the whole point. And so it's very easy to get an artifact free record. It's much more difficult to convince people that that is the correct artifact free record. And that's where we kind of brought in various bits of machine learning. So we've investigated a number of different signal processing algorithms for removing the artifacts from EEG data. And I won't go into the math details of that. And of course, what we looked at is doing multiple different levels of verification. And the last one is machine learning. So looking at what can we do with our machine learning based techniques for verifying whether we've got correct data or not, rather than doing the artifact removal itself. But just before I get to those, so I mean, some of the things we looked at firstly was making a test phantom. So this is a gelatine head. It's got electrodes inside it, so we can play out a brain signal. And of course, that means we know what we're meant to be recording because we're inputting it. And then we apply stimulation to our phantom head and can use this to get the artifact corrupted signal, clean it with algorithms, and see if we get what we want. And we can see here that using, we've got two different techniques here, one called SMA and one called AF. I wouldn't worry too much. We can get very nice reconstructions of the signal that we inputted.
Alex, just a heads up that we're at 20 minutes now, so if you could round off fairly quickly, that would be great.
Yep. We then looked at kind of on-person testing, and we get nice looking signals. So the SAM is when we don't do any stimulation. This activity at about 31 seconds is called alpha. And broadly, with the SMA in particular, it's working. These aren't simultaneous recordings, so we don't expect them all to look the same. What we expect to see is some nice alpha activity at 31 seconds, and that's what we do. What we did with machine learning was to say, well, can you tell the difference between what is artifact corrupted data and what is not artifact corrupted data? To try and get it to learn what does a good EEG signal look like. So for doing this, we gave people two different behavioral tasks to do. So exercising different aspects of your working of your working memory. And we had to do a task while they were stimulated and while they weren't stimulated. And then also just before the task, doing a background activity. So that's what's called baseline. And if you train a classifier, we can tell those four different parts of the experiment apart. So we can tell if someone was being stimulated during baseline or stimulated during the task. And that's what we would expect. Because if there's loads of residual artifacts present, then it should be dead easy to tell if someone's being stimulated or not. It's usually quite easy to tell if someone's doing a working memory task or not, if they're in task or baseline, because they're in the because the brain activity is different when you're doing a task. Importantly for the machine learning, we can tell the two different tasks apart. So we're detecting different brain activity relating to the different tasks that somebody is doing once we've removed the artifact that's present due to stimulation. And so either kind of residual artifacts, if there were residual artifacts that were present, they would have to be correlated with what task somebody was doing. And because there's no physical or kind of engineering reason why that would be happening. And I think I draw a line under what I'm talking about there. But I thought this was quite a nice example of using machine learning, not for machine learning itself, but to help us achieve some of our other aims. Because I'm extremely bad at timetabling, I've got loads of slides about edge machine learning. Right? If you want to implement your algorithms in a wearable device in hardware or on a companion mobile phone, essentially we can do it. We've got a number of different implementations now, and I'll leave that for next time. So, thanks, Niels.
Right, thanks, Alex. I think we've got time for one or two quick questions. So any questions for Alex? I have a question myself, actually. And this is a pretty high level question which relates to one of my obsessions that you know, Alex, and relates also to my role in the Pankers Institute. As you know, the Pankers Institute is all about translation of health technologies to clinical practice and societal benefit. And one of the things that interests me is how do we make sure that the things that we do at lower TRL levels are actually translatable? How do we make sure that they actually will fulfill a need? Could you tell us a little bit on, what is the approach of your group in trying to achieve that? What is your strategy?
I think my strategy would be a bit to have several different things going on at the same time, if that makes sense. So I often talk about the balance between technical push and clinical pull, right? And we want these things to line up rather than the technical push going off in some other direction. And I would have tried to address this in my lab by having different projects on different parts of that spectrum. So we've got some projects which are very like the long COVID stuff. That's clinical pull. People came to us and say we need some help, using wearables, getting the data to the right place, and so on and so forth. And we've got others like the flexible electronics, which is much lower TRL, is much more technical push, saying we think this will be useful, and kind of showing it to people, getting feedback. But and there's projects in between those extremes as well. And by having those multiple steps, they all benefit each other. I think trying to do all of that in just one project is really tough.
Yeah, no, that makes perfect sense. Thanks. Okay, so Alex, thanks again. And I'm going to hand over to Will, who's a consultant rheumatologist at the Northern Carolinas and also professor of digital epidemiology at the university. So Will, the floor is yours.
Thank you, Niels. I'm on hospital Wi-Fi, so I hope I don't fade out. Okay, so this is a picture of my somewhat meandering career, starting in clinical medicine and then moving into epidemiology, drug safety, mobile health research, I guess culminating as a generalist or perhaps a series of sort of mini specialty areas. I'm going to start us on this tour where rheumatology, my clinical life, intersects with my drug safety research. So here you can see a picture of prednisolone, which is one type of glucocorticoid or steroid. Steroids led to the Nobel Prize being awarded in the 1950s. It's widely used in inflammatory conditions. For example, around half of patients with rheumatoid arthritis use steroids, all patients with polymyalgia rheumatica. So this is in rheumatology. Lots of other specialties use lots of steroids. There are clear benefits, but steroids are also associated with a whole load of harms: weight gain, insomnia, glaucoma, cataracts, osteoporosis, fractures, infection, diabetes, etc. There are international guidelines as to how we should use these drugs given their benefits and harms. And the first recommendation is that the side effects of steroids should be considered and discussed with the patient before steroid therapy is started. So this is recommendations from 2007. So let's be a fly on the wall of a clinic in 2007. So if you look carefully, the fly's in the top right-hand corner. Here's a rheumatologist talking to their patients and saying, at your age, the chances of side effects of these steroids are low. And at this dosage, the risks are lower than at higher doses. So don't be alarmed. And the patient says, okay, but just how high is the risk of infection? And I think if you'd asked 100 rheumatologists, as I did at this time, very few, if any, are able to quantify this risk. But epidemiology can come to the rescue. Epidemiology allows us to study groups of people who are exposed to things, for example, steroids, compare them to groups of people who are not exposed to things and follow them forwards in time to see if they have an event such as an infection. So we can see whether steroids increase the risk of infections. We can see what the relationship is with dose. But if you think about the patterns of steroids that we prescribe in clinical practice, you can see that we give steroids via a range of different routes, injections, tablets. The tablet dose varies with time. And if you then get an infection at year 4, how do you link that to that weird pattern of steroid exposure? Well, historically, people have modeled steroid exposure in a whole range of different ways. Mathematically, you can look at a binary measure of current use or recent use or ever use, or you can look at current dose or recent average dose or peak dose or cumulative dose. But all of those make assumptions that we know to be wrong. I spent a year at McGill University when I was writing my application for an MRC Clinician Scientist Award about the safety of steroids. And in that application, I wrote that I would tackle this problem of time-varying drug exposure. But at the time, I didn't know how it would work. I didn't know what the data science or the statistics would be behind that. I attended this course in the MSc that was Advanced Modelling of Survival and Other Multivariable Data that was led by Michal Abrahamovich, really brilliant biostatistician. And I think this was really what kind of kick-started my interest in more advanced analytical methods. Michal had generated this statistical model for a weighted cumulative exposure where the cumulative effect of exposure was modeled as a weighted sum of all past doses, but where the weights represented the importance of the doses as a function of time elapsed. And the model decided what the weight should be. And it's truly brilliant work. Collaboratively with him, we looked at the risk of infection. We found that current doses were most important, but historical doses also mattered. And the really brilliant thing about this was that you could plug in any pattern of steroid use. You've seen that people take all sorts of different patterns, but you could put in the dose, you could put in the duration, you could put in when it was started and stopped, you could compare it to anything else, and it would come out with a relative risk. So if we go back into the clinic, and this is what we've seen before, previously, the doctor fudged the answer. After this research, the doctor's able to say this: around 4 people in every 100 get a serious infection per year. And if all of those 100 took 30 milligrams for 1 month, there would be an additional 4 infections. And so that's the first example of a few examples that I'm going to talk about at the intersection of clinical care and health data research. So broadly speaking, in clinical care, we have questions that are important for health. And we hope that research will give us answers to those questions that are relevant, interpretable, and actionable. But in the middle, across all of these different specialties, these medical specialties, comes data science. So to answer these questions, we collect data, we curate the data, we analyze the data, and hopefully we present it back in a way that is actionable. Now, this happens across all sizes of all scales, from omics data, from molecular, cell, tissue data, right through to population and environmental data. And the space that I work in is population health data, but all of this data science is relevant across the board. The data sources that I tend to use are electronic health records, but then increasingly expanding out to other digital data sources where people are able to provide information that are relevant for health research. So I said I'd talk about relevant, important questions. So here's the first question. How common is rheumatoid arthritis? A patient comes in and says, oh, I've got this. Is this rare? How do we know the answer to that? Well, we have to measure how many people have rheumatoid arthritis in the population. Or we could go out and survey everyone in the population, but that would be a big task. We could reanalyze electronic health records where we record what happens. GPs do this, they code their data, but for rheumatoid arthritis, we know from studies that about 50% of codes for that are wrong. There's lots of different types of arthritis and some of them are incorrectly coded. Hospitals provide the gold standard diagnosis, so let's just analyze data from hospitals. So here I am in my clinic, a global digital exemplar hospital with slightly flaky Wi-Fi. At the end of a clinic visit, I'll dictate a letter and it turns into this free text document that you can see on the right. Now, if I could analyze across all of these letters, I could find how many people had this diagnosis. But these letters we've been text mining outpatient letters to convert this free text information into coded structured information. And here you can see grants from both the EPSRC and from a health charity, Nuffield Foundation. Let me move on to smartphones and wearables. So overlapping with Alex's talk, hence us coming together, I think, today. And this area is really exciting. It allows us to do research that we haven't previously been able to, collecting data directly from patients rather than asking doctors. Why is it better? Well, we can collect new types of data. We can collect digital versions of paper-based forms, but also self-reported information in different ways, novel sensor data. We can then link that to NHS data to further complement it. We can collect time series data more frequently, integrated into people's lives. We can reach a larger number of potential research participants. Just think about the COVID Zoe study that recruited 4 million people. We can intervene through those same devices and digital interventions. And we can change the way in which we design our studies and analyze the data. Well, so what? So what if we can collect all of that data on a bigger scale? What does that allow us to do? Well, there's 6 categories of research question that I'm going to touch on. So the first is descriptive. Can we understand how disease changes through time? What are the day-to-day variations in disease? We've not previously known that. We've asked people at 6 months, how have you been in the last 6 months? And patients say, all right, thanks, doctor. How many flares did they have? How many flares did you have? Oh, 3. And that's our understanding of chronic disease. This study, the remote monitoring of rheumatoid arthritis, or Remora, we've had people tracking their symptoms via a smartphone app. And then uniquely, we've integrated that data into the electronic health record, first at Salford Royal only, and now scaled up to many different hospitals. What we found in the first study was that patients and clinicians all liked it. And so now we're moving on to a larger scale study that I'll talk about in a while. The second type of question is etiological. So we're interested in causal relationships between exposures and outcomes, really the bedrock of epidemiology. But we're now able to look at things that are changing day to day as exposures and symptoms that are changing day to day as the outcome. So here's a question. Does the weather really affect pain? It's a myth, an urban myth that you'll have heard about. Here's a Google search from last night. Does the weather affect arthritis? Above the second most common answer, does the weather affect Wi-Fi? But we didn't answer that one. We answered, does the weather affect arthritis? We ran a national smartphone study called Cloudy with a Chance of Pain. We recruited 13,000 people from across the country, from every postcode area, and collected a massive number of symptom scores because we asked people to enter 10 symptoms on a daily basis for 6 months or more. But these types of study are difficult because, as we all know, people don't necessarily stay engaged with smartphone apps. So this is not related to health. This is just industry standards. On day 1, after installing an app, only 3 in 10 people open it. And by the time you get to day 14, you're down to 1 in 10. what are the implications for health research if you study out? Well, as we started this study, we knew engagement was going to be a challenge, and so we wanted to look at our engagement patterns. And this is what you get. Here's, you can see a line per user in the study. 1 dot is a day on which they engaged, and there's all sorts of different patterns. And one of the reasons I'm showing you this is because it was my first exposure to the Alan Turing Institute, because we took Cloudy with a Chance of Pain data to the Alan Turing Institute summer school, and we had 3 PhD students work on the project. And David Selby, who was then a PhD student at Warwick, and now a research associate with us in the Centre for Epidemiology versus Arthritis, David worked on the engagement patterns. So he took this data, he ran a hidden Markov model, identifying periods of high and low engagement, seen in dark and light grey. And then he clustered them so you could see periods of high engagement in red, medium engagement in purple, low engagement in green, and then what we call the tourists here in blue, people who just entered data for a day and then cleared off. 1 in 7 participants were high engagers. Now, all of this matters because in epidemiology, we need to understand whether there are biases. Are there biases of who we select into the study? Are there selection biases out of the study? And so David's work on clustering allowed us to study that across the population. And what we found was that the tourists were slightly younger, as you might expect, were proportionally more men. But importantly, there was no difference in their beliefs about the weather-pain relationship. Therefore, we didn't believe that this would influence the results of our analysis of the weather-pain relationship. So the analysis was difficult, as you might imagine. We've got changing weather variables through time. We've got changing symptoms through time, lots of people dropping in and out through the study. We had to add into our team some of the sharpest minds in data science. So Malcolm McClure from Vancouver, he introduced the case crossover design, he invented it. He kindly joined the team, as did Antonio Gasparini from the London School of Hygiene and Tropical Medicine, who's doing kind of modern interpretation of Malcolm's case crossover design for a mobile health era. So here's the publication from that study. And just to show you what happened on the day of release, we were the 6th item in the BBC News here. Pain more likely to feel pain on, people more likely to feel pain on humid days, which really shows that this data science matters, a real public interest, and we had tons of response from the public to the results and people sharing their stories. And if you note carefully there, we were 2 points ahead of the 8th news story, tiger poacher who ate bear penises was arrested. So we did well to get above him. In clinic, in fact, today in clinic, a patient asked me this: how much physical activity can I do, doctor, without making my symptoms worse? How much should I do? And I say things like, well, do as much as you can, but not too much. And that's clearly not at all helpful. I'm going to introduce this study, Watch Your Steps, which overlaps with Alex's work here in wearables. This is a smart watch study that we did in partnership with Google Fit. Really just a feasibility study to know whether we could track symptoms on a smartwatch face and also pull sensor data out of the back of the watch. We really pushed the limit of how often we ask people questions. You can see here that we're asking people over 20 questions per day. David, now no longer an intern at Warwick, but a postdoc with us, he updated his engagement patterns here as a ridge plot, and you can see that the engagement's pretty good, but variable across the cohort. Here you can see 3 highlighted participants and their pain level, but lots of people contributing pain that's going up and down. But the big question is, when we see changes in pain, as you can see in the Mr. Blue here in the middle, is that caused by something? And is it caused by something we're measuring? Perhaps they did more activity that led to an increase in their pain. But we're tracking their patterns of activity through their wrist-worn device. And so we're just starting to analyze this data now to see if we can spot patterns of physical activity that might exacerbate symptoms. And the long-term goal here is that we want to be able to automatically guide people as to how much activity they do, having learned what their personal relationship is between their patterns of activity and their symptoms, so that they can do enough, but not too much. So the third question here is predictive. Can we identify real-time predictors of changing patterns of disease to enable just-in-time interventions? So people's symptoms go up and down, they're fine most of the time, but sometimes they struggle, and that time at which they're struggling, they could really do with some help, and help that they don't really need the rest of the time. So can we spot that when it happens, but ideally can we spot it just before it happens? So you've seen the Remora study before that I've introduced. At the bottom here, you can see a pain timeline. The red boxes are weeks on which patients said that they'd had a flare, and you can appreciate that the pain has been increasing up to this point in this one patient. And the idea is that we could spot the pre-flare period and deliver a digital intervention via the patient's own device, such as coping strategies and how to manage a flare. We've got a grant application in at the moment to do just that. The fourth type of question is interventional. So does that digital intervention that we've just delivered through the device, does that lead to improved health and well-being? Well, we've linked the data to the NHS data. We can measure the outcomes. Does it lead to an improvement in disease activity score, or a reduction in the number of flares, or a reduction in disability? We will now be able to analyse that. The fifth is personalised. Can we examine etiological and predictive research questions, not across the population, but within the individual? I'll take you back to Cloudy. We found that there was an association with humidity, as you saw in the BBC briefing. But this is work led by Belay Berliana in the centre. And he found, as you'd expect there with humidity, that there are people who are individuals who are very sensitive to humidity, and very few who are sensitive to it being dry. Across the population, we found no association with temperature, and yet lots of people had told us that they found their pain to be better or worse according to whether the temperature was hot or cold. And when Belay ran this analysis, we indeed found that there were lots of people who were sensitive both to the hot and to the cold, which is what patients tell us. So we are finding what we would expect there. The last point here is about health data, health services research. So does this technology, studying the use, uptake, delivery, costs and outcomes of incorporating patient-generated data into clinical care, so does it matter? And that's exactly what we're doing in the Remora 2 study. So we've proven that clinicians and patients like it, and we now have some NIHR funding through a program grant to run a step wedge trial across all of Greater Manchester and Northwest London, randomising people to either usual clinical care or symptom tracking, and seeing whether integrated symptom tracking leads to better outcomes. So thank you. Just about made it to the 20 minutes. Hopefully summarising that data science is important for health research and clinical care through a series of research questions, and there are more research questions to come. So thank you very much. Made it all the way through the slides.
Many thanks, Will, for a really inspiring presentation. The floor is open for questions. I'm sure people must have questions about this tiger poacher who ate the bear penises, right? I mean, I have lots of questions about that. If not, I do have a question actually, which is kind of the inverse of the question that I asked Alex. So in the wearable space where Alex works, there's just constantly lots and lots going on in terms of new technology. So every time I hear Alex speaking, for instance, I hear new things that I wasn't aware that they were even possible. So for you, as someone who's coming very much from the applied end, from what patient needs, how do you and your group keep track of what the technology actually has to offer so that you can make the best match? Is that something that you consider or look at?
I think the way to answer that is that in clinical practice, you kind of have an understanding of what is it that we need to do a good job, right? So in order for me to make the right decisions about how to treat my patients, I need to know how their disease has changed through time. And you can measure that in all sorts of different ways. You can ask the patient, you can ask them to track their symptoms, but in rheumatoid arthritis, as your disease gets worse, your physical activity patterns change. You do less activity because your joints hurt. Now, sensors can track that. So wearables is a big opportunity for musculoskeletal disease like it is for neurological disease. So there's a need, because I don't currently know exactly how people's disease changes. So wearables could help. But the outputs of it need to do what I need them to do. So it needs to be clinically interpretable. And I think that is the big kind of chasm at the moment. So we can measure stuff and we can show that there are associations, but actually, can we translate it into the clinic? Well, you need to think from the perspective of the clinicians in this instance. But you may take a different perspective. How's it going to help patients? Well, what is it the patients need? And let's build it in a way that's useful for them.
Yeah. Yeah, no, that makes sense. Any other questions for Will? If not, I would like to thank both our speakers again for their fantastic presentations, and thanks to all of you for attending and listening today. Thanks.